Welcome to classwork 8.5, textbook section 6.5. Today we're going to be talking about complex numbers. So first, recall a complex number. You did this a while back in Algebra 2. That's a plus bi. And essentially there are always two pieces. There's the real part, and then there's the imaginary part. Now today we're really going to elaborate your understanding about this. So what you have to understand first is this form is actually called rectangular form. And by rectangular, it means we can actually link this to a plane. So notice how this plane, I put it on your paper. This was the y-axis. Now it's actually the imaginary axis. That's I. And then what was the x-axis is now the real axis. Okay, so think of this as x and y, just real and imaginary. So for the first example, plotting it is really what you think intuitively. For A, this 3 plus 4i, that really just means 3 right and 4 up. So let's just go here. 1, 2, 3, 4 up. There's letter A. So it's exactly like x and y thinking. You just think real, comma, imaginary now. So again, your idea, just think real, comma, imaginary. Same idea. So for B, I'll do this in orange. -1 minus 2i. Let's go 1 left, 2 down. There's your B. Part C I'll do in blue, -3. So notice how it's only the real part. So I'm going to go 3 left. And then the last one I'll do this in red, -4i. That's only the imaginary part. So I'm going to go down 4D. And we're done. We've plotted our first points in the complex plane. And again, this is the complex plane. So different from the real plane. So now it says find the absolute value. Everybody highlight that. Absolute value of a complex number. So I want you to recall the idea of absolute value is simply the distance from 0 on the number line. That's the basic idea of absolute value that you've used for your entire math career. So now we're actually going to use it in the complex plane. So look at A, 3 plus 4i. We graphed that earlier. That's going to be right there. 3 right, 4 up. Now if you think about the distance from 0, 0 is right here. So what we're trying to find is this diagonal. This is going to be the absolute value of 3 plus 4i, because that's how far you are from 0. So to do that, all we're going to do is some basic geometry. Think about this triangle right here. This is 3. This is 4. 3, 4. So we're just going to do the absolute value of z must be the square root of 3 squared plus 4 squared. It's just a Pythagorean theorem. That's a square root of 25. Absolute value is 5. So if you want a formula, I can just write the absolute value is simply the root of a squared plus b squared. And again, that's basically your Pythagorean theorem. So for b, -1 minus 2i, for this one, we're looking for how long that leg is right there. So let's just do it. The absolute value of z, we'll just do the root of -1 squared plus -2 squared. That's going to be the square root of 5. And there we have it. Absolute value done. Okay, example 3. Plot this number in the complex plane, then write in polar form. Okay, so first let's just plot it. Let's take care of that. That's easy. So we're going to go 2 left and 2 down. 2 left, 2 down. There's our dot. Now this is new. This is polar form. So first, let's recall rectangular form. A plus bi, that's what we started with. This is called rectangular form. Now there's a new form. Z equals R cosine theta plus I sine theta. Right here, this is what we call polar form. So this is going to be new for you, so make sure you write this down. And if you think about it, it's actually quite simple, because if I were to distribute this, you get r cosine theta plus I sine theta. Essentially, this piece is like your x, or your real portion. Oh, and I forgot the r here. And this piece right here is your y, and that's like your imaginary portion. So really it's just like your polar facts, r sine theta, r cosine theta. We're just writing it r times cosine theta plus I sine theta. Okay, so that's our polar form. And again, make sure you highlight this. We're going to use this a lot in this particular unit. Now you're probably wondering, okay, now how do I use all that? So the first step we're going to do, we're going to find the absolute value of z. We got to find that distance. This thing right here. So it might help to draw a triangle. So I'll draw a triangle. We know that that's 2, negative 2, negative 2. So I'm just going to write on the side here the absolute value of z. If they're both 2, then we know that should be 2 root 2 by the Pythagorean theorem, or special right triangles. So if you look at the polar form, we're actually halfway there. Z equals r cosine theta plus I sine theta. We already found r is 2 root 2. And again, that's just finding the hypotenuse. Or think of it like polar, how far you are from the origin. The only part we don't have is this theta, so I can just write this in. Cosine blank plus I sine blank. To find it, it's just like our polar coordinate unit. We want to find this rotation. So some of you might already know the answer, but in case you forgot, we can just do some basic trig. Let's just do our polar fact. Tan of theta, we're going to find tan theta of negative 2 over negative 2, which is tan theta of 1. So theta must be pi over 4 and 5 pi over 4. But we can see this is quadrant 3, which means we deny pi over 4. There's our answer, 5 pi over 4. So you write that in, and there is our polar form right here. Now that is a lot to write, so for shorthand, I will accept this, and this is what some people often do. They write 2 root 2 kiss 5 pi over 4. And KISS meaning CIS, that just stands for cosine I sine. And it's just a shortened version of the formal one up here. But both of these are helpful. I like that one just because it's a little bit faster. So for our next example, notice how it just says write a complex number in rectangular form, which means this is our polar form right here. There's polar. Our goal is to get to rectangular. And rectangular, recall, is just a plus bi. So let's just do basic trig. 2 cosine 60 is 1/2 plus I sine 60 is root 3 over 2. Let's multiply. That's just 1 plus I root 3. Or some people write 1 plus root 3i. Both of these are perfectly fine for me. And you're done. Either one of these is perfectly fine. Now here's the next part. So this next part, notice there are a couple of notes here. So we're going to first talk about the product rule. So I recommend you just take a minute to pause the video and just write down the product rule. I'm not going to prove it to you because the proof is actually pretty cool. I'm just going to offer extra credit for someone who can prove the following 2 rules. And again, extra credit will apply to everybody. I just need someone to find why it works. So after you've written those rules down, make sure you write it. You pause the video and then unpause once you're ready. Okay, now that you've paused it, the product rule for complex numbers is super cool. Essentially, if you're going to multiply these, all you have to do is multiply the 2 outside numbers. So 4 times 7. Make this a little bit nicer. So if I want z1 times z2, the outsides multiply together. And then we're going to write kiss. And the insides just add 50 plus 100. So that's 28 kiss 150 degrees. And that's it. Now my math lab, I don't think they can take that notation, so on your homework you probably have to just write it out. 28 cosine 150 plus I sine 150. But again, for doing test quizzes, you can just write the KISS version. I like that version better. Now the quotient rule, same thing. Pause the video, write down the rule. Once you're done, unpause the video. Now that you've written down the rule, again, the quotient rule is pretty cool. All you have to do if you want to divide these is you divide the outside, so 12 over 4, then write KISS, and the angle subtract. 3 pi over 4 minus pi over 4. So that would be 3 KISS pi over 2. And you're done.